First of all, this video assumes that you understand electron configuration at least to some kind of a passable degree. So if you haven't fully come to understand electron configuration or how it works with the periodic table, I would highly recommend that you review it before you continue watching, or at the very least, if you think you have at least some relative understanding, then by all means keep watching the video. The whole point of this one is to essentially show where the octet rule comes from, why it is called the octet rule to begin with, and why really it only deals with the valence electrons. And this one is going to get kind of involved because I'm really going to go through the insights as to how it actually shows up. And the only way you're really going to be able to understand the pattern is if you're able to tie electron structure to pretty much what the configuration is. And what I mean by structure is I mean the shell model of the atom. So in front of you, you have the periodic table, and really, so most of it was already covered in a way that I needed it to be, but I needed to highlight the other parts of it that you can use to figure out what kind of configuration you can find for your element of choice. You can pick one and then you can slowly work your way there. In the blue, what I've highlighted with blue is essentially groups 1A and 2A, so the alkaline metals and the alkaline earth metals, and then helium. Helium actually belongs to the s block, and the reason for that is because it only has the s orbital, and that's why. Now, what I highlighted in orange is called the p block because that's where you have all of your p subshells. What's in yellow in the middle is again the transition metals, and then what you have pretty much down at the bottom is what's essentially called the F block, which is your lanthanides and the actinides. Your transition metals are your D block. You don't need to worry about the lanthanides and the actinides at all. F block is not being touched, but you do need to at least have some foundational knowledge of how D block works. And so again, this only really makes sense if you have some level of understanding of electron configuration. Now, octet rule. Why is it called octet rule? Well, the best way to explain this, first of all, is to pretty much show shell models of an atom. And so I'm going to do that by pretty much showing the most simple and basic ones that you can ever consider. And so shell models usually are very straightforward. What they do is that they have a nucleus in the center, and it can be represented by pretty much any kind of a circle that's filled in. And then they begin to show the shells around. And remember, each period on the periodic table, so each row is when you add a new shell. The first shell, because it's only made up of an s orbital and it's a single orbital, each orbital can only hold 2 electrons. And so it just so happens that when you talk about the first shell, when it's filled, it can hold 2 electrons max. Now here's the issue. Due to quantum mechanics and stuff I'm not really going to get into, this is more called the Pauli exclusion principle, but the whole idea really is that it's just a very complicated way of saying that electrons really like to exist in pairs. So pretty much more often than not, when you have a filled shell, it's going to be an even number of some kind because it's going to be going by 2s. The first shell can only hold 2 electrons. The second shell, when it's filled, because once you actually have that first shell filled up, the second shell can actually hold 8 electrons max. And then by the time you pretty much get to the third shell, what's going to happen is that it can actually hold 18. And once you get past that, the fourth shell can also hold 18. And then it starts to get more complicated from there. And that's not something that I'm really going to struggle with. And that's not something I'm really going to cover. All you really need to know is have this idea that when you have a filled shell, you need to move on and you need to start filling the new one. So, actually I need to count because I already lost count. That's 8, 9, 10... 11, 12, 13, 14, 15, 16, 17, 18. So that's what you would have if you had a full third shell. Ideally. But see, the thing is, the electrons don't actually fill that way. The issue, and this is where a lot of people kind of miss it, is that the idea is that the more you fill a shell, the more stable the electron configuration is. And stability is one of those things that really drives the processes in nature. And so the more stable something becomes, the better it is. The less energy you need, so on and so forth. And so what that means then is that if you think about it, because every single time when you go back to the periodic table, because every single time you eventually get to the noble gases, which I'm going to mark with an arrow, so these guys, those noble gases, every single time you get there, that's when you fill a shell. And then once that shell is filled up, when you pretty much move over, so like let's say when you go from helium over to lithium, because that's how you have to count it, you're starting to fill a new shell. Okay, well, here's the idea. If we look at the configuration for helium and we were to think about how it looks like in the shell model, which I'm going to have to kind of reset it, helium is pretty much at the end of the first row, and that means it only really has that first shell, or the first period. That means it's going to have 2 electrons. The shell that it has on the outside is really the valence shell. And remember, the valence shell is the outermost electrons. Those are the electrons that you have the most access to. And so really, when you write the electron configuration for helium, it's going to be 1s2, because again, you're just filling in the 2 electrons in the s orbital, and then you're pretty much done. And really, the interesting thing is that when you actually write the Lewis dot for helium, you actually write it like that. You don't actually keep the dots separate, because here's the thing. You only have that one shell. Helium only has 2 electrons because its atomic number is 2. And it just so happens that because those 2 electrons are in the same orbital, they're paired up. And so that's why helium is never really written as having 2 separate electrons away from each other. It's actually paired electrons that are already paired up, and they don't really want to mess around with anybody. They're just kind of there. Okay, well, that's helium. Well, what if we kind of add another shell? Because if we add another electron, we're forced to add another shell, because again, the first shell can only hold 2 electrons. Well, if we go into the second row, and then eventually we kind of move along to the ending, if we keep going along and we write the configuration for neon, which I'll circle right now, so for neon, it's going to be essentially, and again, this is why this video assumes that you have knowledge of electron configuration, it's going to be 1s2, 2s2, 2p6. Now, here's where things should start to click if you're really focusing on paying attention. That means that if you kind of count along, neon has 10 protons, which means if it's neutral, it's going to have 10 electrons to balance those 10 protons, because the negative charges have to balance out against the positive charges. And so that means then that when we draw the shell model for neon, the valence shell is now the outermost shell, which is the second shell, whichever one you're on. And so that means then that when we think about the electrons on the valence shell for neon, we have 8. 1, 2, 3, 4, 5, 6, 7, 8. And then it's filled. And then you're pretty much done. And again, that should make sense because, look, if you look at the electron configuration, the outermost energy level is the second energy level, which currently right now is being made up of the s and the p orbitals put together. And it just so happens that when you look at how many electrons can actually fit into the s and the p, you get 2 and you get 6, which if you do 2 plus 6, you get 8. 8. Octet. Okay, this is where everything should kind of start to click if you're really focusing on trying to understand this. So, if we were to go on to the next shell and we were to think about trying to have a general idea for what the next noble gas would be, which is argon. That's the next one that we're going to be looking at. So for argon, you need to be thinking about the fact that argon is number 18 on the periodic table. That means it's going to have 18 electrons, right? So if it has 18 electrons and it's in the third period, and you can see that because, again, third period, right? Okay, if we're talking about argon, then that means that we're going to have that third shell, and so we can show that this is now going to be our valence shell. These are going to be our valence electrons. Okay, so then what does that mean then? Well, if we're looking at now the outer electrons, the outermost, the valence, the bonding electrons, whatever you want to call them, we can basically focus on the configuration. So if we look at where neon is at, we're going to need 18 electrons, and when you run through, you're going to be going 1s2, 2s2, 2p6, 3s2, 3p6, and that's going to be the configuration. And that's what we're going to have to write. And that is actually going to give us a ton of information, because when we write it down, 1s2, 2s2, 2p6, 3s2, 3p6, again, you're only looking at the outermost energy level. It's the third shell. So how many electrons are you going to have in the third shell? Well, we repeat the same thing that we did last time. All we need to do is look at the numbers that have 3 in them, because it's our outermost shell. And then we realize that we have 2, and 6, because again, the S and the P are the outermost levels, and they are the highest energy levels that are actually in that outer shell, and they essentially tell us how many valence electrons we have. So 2 and 6, that makes 8, which means for right now, even though technically speaking, the valence, or not, sorry, the third shell can hold 18, at least for right now. When it fills up, before we move on, we actually fill in those, and so we have 8 done. Okay, fine. But then see, this is where it starts to get a little complicated, and I think this is where people kind of lose it. But the beauty about what I'm about to show you is that if you can make sense of it, it tells you why the octet rule works the way that it does. And so what that means is that we need to skip ahead to the next noble gas to think about what that next full configuration looks like. And so for that one, we need to look at krypton, number 36. So we have 36 electrons now. In order for us to make sense of this, we have to think about the configuration again. And so again, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now this is where things get interesting. 3d10, 4p6. So we went 4s2, 3d10, 4p6. Okay, what would that look like if we kind of fill in on the shell model? Because we need to think about that as well. And so this is where you want to make sure that you pay very close attention. So we have 36 electrons that we need to fill. So let's think about what the configuration is going to be for argon. Again, it's going to be, I'm going to draw this lower, that way I have more space, but pretty much it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then again 3d10, 4p6. Okay, why is this important? Well, because here's the thing. If I were to do a shell model based on the configuration, right now what we have in front of us on the shell model right above is pretty much that. The configuration that we had for argon. Sorry, we're working on krypton right now. I forgot about that. That would be the shell model that you're looking for argon right now. But the problem is we need to build it for krypton, so we kind of need to go based off of what the configuration tells us. So if we go off a simple shell model, look, here's the issue. We're at 3p6 and then that shell is full, which means when we move on to 4, we need to start filling that. So that means we need to make the fourth shell. So there's the outer energy level. So now that's the valence shell, number 4. And then you have, so far, again, 2 electrons because 4s2. So I'm going to go ahead and put that pair there. So there you go, 4s2. But then remember, we had to start going to 3d10, which means the next 10 electrons that we're going to put into our shell model actually have to get put into the third shell. So let's check that. Well, that means that the next 10 electrons that we put in there, again, have to go into the third shell. So 1, 2, 3, 4, 5, 6, 7, 8, and then another pair somewhere, let's say 9, 10. Regardless, that's kind of the idea. That's completing 3d10. But see, look right now. Right now, in terms of valence electrons, we aren't counting any of the d electrons because they're in the third level. The third level is no longer the outermost shell that we're working with. It's still 4, which means when we get to 4p6 and we start thinking about what that means the next 6 electrons, when they pair up, have to go into the outer level. And so what that means then is that when we write those, we're going to have, there's 3, 4, there's 5, 6, and then there's 7, 8. And once more, we end up with 8 electrons in the outer shell. And this pattern will continue to repeat. It doesn't necessarily matter about the fact that the third shell can hold 18 or that the fourth shell can hold 32 at max. That's not the issue. The problem is that no matter what happens, before you can begin to fill another shell, you're actually going to have 8, which is why when you think about it, if you focus on the fact that the outermost energy level is a 4s2, and it's also the 4p6, when we get to the end of the table, which is group 18 or group 8a, whatever you want to call it, they have what's called an octet, because that is the maximal stability that you have before you essentially need to start opening up a new shell. And so what that means then is that most elements like to do whatever they can to essentially complete an octet, which is why when you do a Lewis dot, all you're really looking for in the Lewis dot is essentially trying to understand how many valence electrons you have currently on that atom, because again, you're only focusing on the electrons in the outermost shell, and that's it. And it just so happens that because the pattern repeats itself, so let's say that we look at the periodic table and we're talking about, well, I don't know, group 16, so oxygen. I'll draw the rest so you can see that. Because the pattern repeats itself, if you're looking at oxygen or sulfur or selenium, they're all going to have, let me actually erase that. They're all going to have the same Lewis dot essentially in terms of actually drawing the dots, because again, the pattern repeats itself. They're all in group six, and so that means that the outermost energy level is only really going to have 6 electrons. And so that also pretty much tells you then that when you think about it and you move on to the octet, the reason why everything wants to have an octet is because they want to fill essentially what are their s and their p orbitals. That way they have as much stability as humanly possible, which is why most elements generally are trying to essentially copy the stability of the noble gases. And so the octet rule again comes from the fact of that when you focus on the configuration, it really just comes from the 4s, or sorry, not the 4s, but pretty much any s and any p. And so again, just to kind of repeat myself, 2 plus 6 is 8, and that's how we have the octet rule. I hope that made it a little bit clearer if you really wanted to understand it to a better depth at least.